Chapter 9: Photoelectric Effect. We have seen that a metal surface will, if provided with appropriate amount of heat energy, emit electrons. Radiations of appropriate strengths can also have a similar effect. When an electromagnetic radiation of sufficient frequency is radiated on a metal surface, electrons are emitted. These electrons are called photoelectrons, and the phenomenon is known as photoelectric effect. Consider this setup on the screen. This can be used for experimental studies of photoelectric effect. It has an evacuated glass tube or a quartz tube having a photosensitive plate labeled as C. This is known as the emitter. Another metal plate A, which is known as the collector. Now the emitter and the collector are attached to a battery that maintains the potential difference between the plates. There is a small window that opens into the glass tube. It's a transparent quartz window. This permits UV radiations to pass through it and irradiate the emitter. Now a monochromatic light from a source and of sufficiently short wavelength passes through this window and falls on the photosensitive plate C. Because of photoelectric effect, electrons emitted by the plate C are attracted and collected by plate A. Why? Because of the potential difference created by the battery. When the collector plate is positive with respect to the emitter plate, the electrons will of course be attracted to it. The emission and attraction of electrons causes current flow in the circuit. The resulting current flowing in the circuit is measured and can be seen on the ammeter reading. The photoelectric current can be increased by varying the potential of the collector plate with respect to the emitter plate. The intensity and frequency of the incident light can also be varied. Photoelectric effect can also be observed using a charged electroscope. We have a piece of zinc plate that has been placed on the top of an electroscope and charged negatively using a piezoelectric lighter. When a UV lamp is switched on in front of the plate, the electroscope is discharged, and this is because the photoelectrons emitted by the zinc plate are repelled and the electroscope becomes discharged, so the leaf collapses. However, if the electroscope is charged positively, nothing happens when the plate is irradiated by UV. And this is because the photoelectrons emitted from the positively charged zinc plate do not escape due to attraction by the positive charges on the electroscope, and the leaf remains diverged. So photoelectric effect refers to the emission of electrons from a metal surface in response to incident light. The energy contained within the incident light is absorbed by the electrons within the metal, giving the electron sufficient energy to be emitted from the metal surface. In 1901, Max Planck came up with the idea that light energy is propagated as small packets of energy. Each packet is called a quantum of energy. In light, these discrete amounts of energy are called photons. According to Planck, the energy E possessed by one photon is given by E is equal to hf, where h is Planck's constant equal to 6.63 times 10 to power negative 34 joules second, and f the frequency of the radiation. From the general wave equation, C is equal to F lambda, F is equal to C over lambda. and therefore E is equal to hc over lambda, where c is the velocity of radiation in vacuum and lambda the wavelength. Since the velocity c of the radiation and the Planck's constant h are constants, a radiation of longer wavelength lambda has lower energy. For example, the energy contained in a photon of red light of wavelength 7.0 times 10 to power negative 7 meters will be given by E is equal to hc over lambda, and so E is equal to 2.84 times 10 to power negative 19 joules. Next, we look at Einstein's equation of photoelectric effect. Now, when a photon strikes an electron, all its energy is absorbed by the electron. Some of the absorbed energy is used to dislodge the electrons from the metal surface, while the rest appears as the kinetic energy of the emitted electron. The energy transformation during photoelectric emission is thus summed as follows. Energy of a photon is equal to the energy needed to dislodge an electron from the metal surface plus the maximum kinetic energy gained by the electron. The minimum amount of energy needed to dislodge an electron from a metal surface is called the work function of the metal, W0. This energy varies from metal to metal. The work function is expressed in a unit called electron volt or joules. 1 electron volt is equal to 1.6 times 10 to power negative 19 joules. Emission of photoelectrons will not occur from a metal surface if the frequency of the radiation falling on it is below a certain value. This minimum frequency is known as the threshold frequency F0 for the metal. The corresponding wavelength is called the threshold wavelength lambda naught, the maximum wavelength beyond which no photoelectric emission will occur. The work function is thus given by work function is equal to hf0. This can be expressed as work function is equal to hc over lambda. For any radiation of frequency f less than the threshold frequency, hf will be lower than the work function and emission will not occur. When the frequency of the radiation is f0, hf0 is equal to the work function and emission occurs. When the frequency of the radiation f is greater than f0, hf is greater than work function, and the excess energy in this case appears as the kinetic energy of the emitted electron. Therefore, hf minus work function is equal to the kinetic energy, a half mev squared, where me is the mass of an electron and v the velocity of the electron emitted. hf is equal to work function plus kinetic energy, that is a half mev squared. This is Einstein's photoelectric equation. Since work function is equal to hfo, this can also be written as hf is equal to hfo plus a half mev squared, and hence hf is equal to hc over lambda naught plus a half mev squared. Let's take an example. The minimum frequency of light that will cause photoelectric emission from a metal surface is 5.37 times 10 to power 14 Hz. When the source is irradiated using a certain source, photoelectrons are emitted with a speed of 7.9 times 10 to power 5 meters per second. Calculate 1. The work function of the metal, 2. The maximum kinetic energy of the photoelectron, and 3. The frequency of the source of irradiation. We have been given the Planck's constant and also the mass of an electron. Solution: work function W0 is equal to HF0, and if you multiply that, we shall have 3.56 times 10 to power negative 19 joules. 2. Maximum kinetic energy is given by a half mEv squared. So if we multiply that, we shall have 2.84 times 10 to power negative 19 joules. 3. HF is equal to HF0 plus a half mv squared. We already have HF0, which was equal to the work function, that is 3.56 times 10 to power negative 19, and we also have the kinetic energy, 2.84 times 10 to power negative 19. If we add those two, we get 6.4 times 10 to power negative 19. To get F, we divide by Planck's constant, and if we do that, we get 9.65 times 10 to power 14 Hertz. Factors affecting photoelectric emission. Now, the ability of a radiation to eject photoelectrons from a metal surface is determined by two main factors, namely the intensity of radiation and the type of metal. The intensity of a radiation is the rate of energy flow per unit area when the radiation is normal to the area. Intensity is equal to work over area times time. That is, I is equal to W over AT. But then W over T is equal to power. Therefore, intensity is equal to power over area. Every metal surface has its own minimum frequency of radiation called the threshold frequency F0, below which no photoemission can take place, no matter how intense the radiation is. For example, zinc metal has a threshold frequency of 10.47 times 10 to power 14 Hertz. Any radiation with a frequency lower than this cannot therefore eject an electron from zinc plate. The results on photoelectric effect can be summed up as follows: that the rate of emission of photoelectrons is directly proportional to the intensity of the incident radiation, and that each metal surface has its own minimum frequency for photoemission. Also, the emitted photoelectrons have kinetic energy ranging from 0 to a maximum value. Increasing the frequency of the incident radiation increases the kinetic energy of the photoelectrons. Applications of photoelectric effect. The photoelectric cell. The photoelectric cell, also known as a phototube, is an electron tube in which the electrons initiating an electric current originate by photoelectric emission. A phototube consists of a cathode coated with a sensitive material and an anode. Light falling on the cathode causes the liberation of electrons, which are then attracted by the positively charged anode, resulting in a flow of current proportional to the intensity of the incident radiation. phototubes are either evacuated or filled with an inert gas at low pressure to achieve greater sensitivity. If a series of metal plates are arranged in an electron tube, then the photoelectric emission is amplified by secondary electron emission. This type of tube, where there are a number of tubes, is called a photomultiplier. It is capable of detecting radiations of very low intensity, and hence it is used as a radiation detector in nuclear research. The photoelectric cell is applied in photosensor motion detector used in burglar alarms, traffic light controls, and automatic door opener, whereas certain types of phototubes are used in sound recording, television, and in scintillation counters. Photosensor motion detectors are the devices you see in a store at a shopping mall. When someone enters the store, the motion detector sounds a bell. The two components of a photosensor are a source of focused light and a light sensor. In a home security system, the light produced by a bulb at one end of the circuit falls on the phototube located some distance away, and electrons are emitted by the cathode. When someone walks between the light source and the sensor, the path of the beam is blocked briefly. The sensor registers a drop in light levels and sends a signal to the control box. This box is connected either to a siren, flashing outdoor lights, or a telephone auto dialer.
Time progressed. Into the mid-1800s, telegraphy has been discovered. Samuel Morse has devised the Morse code. They started with telephony, the telephone, sending voice across wires. By the 1890s, things really started to hot up. In those times, guys like William Crookes, various other experimenters, all started playing with this new phenomenon of high voltage using a device called a Rumkov coil and passing this high voltage through tubes that the air had been exhausted from. So in other words, they had removed the air from these tubes and they tried to see what would happen if very high voltages were passed through the slot. Now, there is our cathode ray. You can see the ray appearing across the tube. This is the sort of thing that fascinated the scientists of those days. Now, this is very interesting because this led to all sorts of things. And of course, if you continue to experiment as they were doing, what would happen? Discoveries are bound to be made. And this, of course, led not only to the discovery of the electron, but also the discovery of something that I'm sure a lot of us have had dealings with in one way or another, the discovery of X-ray.